In this video, we're going to give an introduction into iMachining. iMachining is a revolutionary new machining technology created by SolidCAM. So first thing we're going to do is we're going to create a new milling project on this part. We're going to define our coordinate system. It's as simple as picking on the face we want. I like to put my coordinate system on the back left corner, so I'll just shift it there. Accept all my default clearance levels. Going to define our stock, the default is a 3D box, but I already have my stock modeled, so I'm just going to pick it. Same thing for the target. I'm going to just pick that off of the screen. For iMachining, we need to pick our machine, so I'll pick our Haas VF2SS. For our material, we're going to pick an aluminum, and we'll pick our machining level to default to 6 for this project. Now we have our part ready for iMachining, or for operation creation. So what we're going to do is we're going to make our iMachining operation. When defining the operation, the first task is to define the geometry. I'll tilt this part down so we're looking at it as it would be sitting in the Haas. I'm going to pick this outside stock chain. I'm going to pick the part chain. And what I'm going to do is I'm going to tell SolidCAM that that outside chain is open. It's going to change to black. This is going to allow SolidCAM to know that that is material and that it is going to be able to plunge and machine from the outside, and that's also where the stock is coming from. We're going to pick the bottom of our part, which we see is 875, and I'm just going to name my geometry outside. Next, we need to define our tool. We'll define a tool from scratch and show how easy this is in SolidCAM. So we're going to pick a 1/2 inch end mill. We'll say that the tool's going to stick out 1 1/4 inch, shoulder length 1 inch, cutting length 1 inch, and number of flutes is 3. We'll also go and throw a holder on this. So we'll just go pick this 1 3/4 inch, and we will select it. Since we're machining the outside shape of the part, we want to go a little bit deeper. So we're going to go an extra 20 thou past the bottom of our part. And what we can do now is just calculate the toolpath. And go to our simulation. What I'll do is I'll play through this one time first, and then we'll talk about what the toolpath is actually doing. So there's the toolpath to machine that outside shape. We'll go play this in the Solid Verify so we can see what it looks like removing the material. And then once it's finished with this, we'll go back to the wireframe toolpath and we'll show what the different features of the toolpath are. Okay, so the first things we want to talk about with iMachining is what are the main goals we're trying to achieve. The main goal we're trying to achieve with iMachining is to do morphing spirals. What we consider a morphing spiral is a spiral that is not circular, but it is done off of a shape. We call it morphing because unless you have a perfect circle, there's no way to make it go to some other shape. So what we do is we work between a range of minimum and maximum step over, and this allows us to morph to any geometry, not just a circle, and create a spiral, which is keeping the tool in contact the entire time. So what we'll do is we'll play the beginning of this toolpath, and what we'll see is what SolidCAM does is on this outside shape, it is first preparing the corners, and if we look at a top view, it'll help explain what we're looking at. The areas where we have the most amount of material are the 4 corners. Now in the corners where there's the least amount of material, we see it only had to do 2 passes, 2 passes. In this area where we have a lot of material, it's actually going to do multiple passes. And what it's doing is it's actually preparing to do a spiral. Since there's no way to do a complete spiral on this without having the tool in contact all the time, we prep the material. So we're prepping the outside corner. Soon as we're done the outside corner, then we're going to go to what we call our morphing spiral. Well, let's play through 2 loops so we can show something here. There's the first loop, and here is the second loop. Now what we see here is SolidCAM's morphing spiral. In the area that we have the least amount of step over, or the least amount of material, we have the smallest step over. In the areas where we have the most amount of material, we have the biggest step over. So what we do is we work with like a degree of freedom with our range of step over, and this gives the tool the ability to do morphing spirals and keeping the tool in contact the entire time. As we look at our feed rate over here, what we'll see is SolidCAM is also doing feed rate adjustment. So in the areas where there's a smaller step over, we're increasing the feed rate to maintain efficiency. So as we single step through this, what we can see is on the thin areas, we can see it go to 256 inches a minute. As we come to the thick area, we can see the feed rate slow back down to 147 at the thickest point. Continues doing the spiral toolpath, and then at the end, it'll then go and clean out this internal area over here. Now some things to note when we look at iMachining from a side view. There are no retracts. None at all in this toolpath. There's only the one entry and the one exit. So SolidCAM is able to keep the tool down in the pocket and not have wasted machine time rapiding around the part. Now that we went over the toolpath, we want to go over the technology wizard. What our technology wizard is doing is it's actually creating all of the cutting conditions for the toolpath to follow. Feeds, speeds, step overs, depth of cut. How we've created the technology wizard is we've done 3 years of live testing on a complete range of tools, complete range of machines. We've done testing all the way down to 40,000 Zen mills in hardened steel. We've done titanium testing. We've done steel, stainless steel, aluminums. We've used all sorts of different size tools with 2 flutes, 3 flutes, 4 flutes, 5 flutes. We've done different machines. We've tested on Haas's, Mazaks, Hercos. And what we've done is we've developed an algorithm that ties all of that information together. What we're not doing is we're not creating an Excel database of feeds and speeds like many people have tried before. What we're doing is we're actually creating an algorithm where we look at, okay, we define a machine that has a certain maximum RPM, feed rate, etc. Then we have a material which has a certain physical properties to it, and then we also have our end mill, which has so many flutes, it's a certain diameter, it has so much flute length, it even has pitch for the flutes. And then what we do is we devise a cutting condition for that specific condition. So what we'll do is we'll look here and see what we get in the technology wizard page in SolidCAM. What we have is a 3D solid that is showing this step over and this cut for this pocket. The main thing with iMachining is we have this machining slider. What this does is it allows us to go from level 1, which is very safe feeds and speeds and step overs, to a very aggressive feed and speed and step over. As we see in the bottom left corner here, we can see the RPM ranging from 10,000 and 170 inches a minute with a 126 step over, to the lowest portion, which is a 3,200 RPM, 40 inches a minute at 34,000 RPM, or 34,000 step over. Now what's important to note here, as I said before, is this is not a Excel database of feeds and speeds. So let's say, instead of doing this in one cut, which we're doing is 895, let's say we wanted to do 2 depth of cuts. What you can see is SolidCAM is adjusting everything based on what depth of cut we're doing. We can see the step over jumped from the 100 to the 207. If we go back to 1 depth of cut, we can see the 126 at 895. If we do 2 depth of cuts, where we're cutting 475, we go to 207. So in this manner, we can see that iMachining is being very intelligent, and it's trying to adjust for all of the conditions that we change. So every geometry you pick, every depth of cut, every tool that you pick, we're going to adjust feed, speed, step overs, and make sure all of them are synchronized and perfect the entire time. And then we have our machining slider, which is giving you, the machinist, the freedom to pick what works the best. As we know, we can achieve great things. But to achieve high feeds and speeds, we need to have all the right things set up. We need to have the perfect fixturing. We need to have the perfect tooling. We also need to have the perfect tool holders. So what this does is this gives us freedom And what we do is we get less cutting force and those types of parameters as we go less in the machining slider. So if we know our part's not held very rigid, we can pick a low machining sliding. If we know we don't have the part, let's say it's not very rigid in the machine we're holding, just because of the machine it's not very rigid, we can go slower. If we're doing a prototype part, we can go slower. Generally, most of our customers are going to work in the 3 to 6 range, which is just average. But if we know we're holding good, we can go high. And if we know we're holding not so good, or we're having tough times with chip evacuation, or not good coolant in the machine, we can go down to the low end.